Good afternoon, everybody. My name is Kai Grønbæk. I'm head of department here at the Computer Science Department at AU. And it's a great pleasure to welcome you all to this rather special event. It's special both form-wise and also with a very special guest. We have Bjarne Stroustrup visiting here. He's alumni from Aarhus University, and he is also an adjunct professor here at the department. And he graduated 45 years ago in 1975. So Bjarne is today a technical fellow and managing director in the technology division of Morgan Stanley, which is a huge financial business in New York City. And he's also a visiting professor at Columbia University in New York. He has actually been visiting Aarhus for several weeks, and we've been looking for the right COVID-19 window to make this physical talk. And since Bjarne is leaving next week, it had to be now. So I'm very happy that we can now host approximately 60 attendees here in the auditorium, obeying all the COVID-19 regulations, and we will have up to 200 attendees on Zoom. And we will actually also record the session so that people who miss it now can get back later. Bjarne doesn't need a long presentation since he's among the Danish computer scientists who are renowned all over the planet for his research. It's research that has led to the invention of one of the first and one of the most widely used programming languages supporting object-oriented programming, namely C++. And he has received a lot of awards and prizes for his work, including our local Rigmor and Carl Holst Knudsen's research prize some years ago, back in 2010. And the seeds for the C++ invention were actually sown here at the Department of Computer Science when Bjarne, together with fellow students such as Ole Lehrmann sitting over here, were attending lectures by legendary Turing Award winner Christian Nygaard, who gave lectures on object-oriented programming here back in the 70s at the Department of Computer Science. And the impact of this invention is enormous. C++ is heavily used by students and researchers all over the world. And even though you are not a programmer using it directly, you are most likely an indirect user of C++ programs because they are sitting in a lot of products you buy these days: cars, TVs, coffee machines, and so forth. So we all look very much forward to hear Bjarne talk about C++ background and the perspectives for the futures. And a warm welcome to Bjarne. The floor is yours. Thank
you. Thank you very much. I apologize for sitting down, but I was out running in the woods. You can see the woods there. And I twisted over on my ankle and hurt my foot badly. So if I had to stand up for an hour and a half, nothing good would come out of that. And I'll point out that I learned more from Christian Nygaard for talking with him up on the top floor of the old Datalogi building when he was visiting town, and informally chatting with him more than the lectures. He was really good at just talking about things. Talking with Christian was mostly listening, unless you're Christian. Anyway, so I'm going to talk about C++, and I'm going to start sort of with what I and others have been trying to do. And then I'm going to switch to the latest version of C++ that will become official any month now. It is technically complete. It's waiting in Geneva for formal approval by the bureaucrats there that wants to make sure that we use English spelling rather than American spelling and things like that. But apart from that, it's finished. And then I'll go into technicalities for a while, and then say a little bit about the future. And basically, the reason I work with languages, the reason I am interested in this stuff, is what you can do with them. I know this is an academic organization, and sometimes in academia you measure quality with a number of papers written and how neat examples fit in the two-column POBL format. I'm less interested in that. I, by mistake some years ago, got a POBL paper, but that's not my main aim. My main aim is to enable people to write good applications. And so there's some good applications there. And the pictures that I'm going to show on the slides, and mostly not explain, all has something to do with C++. And for people who likes language wars, I'll point out that I don't criticize C++ applications. So we're not going to go there. And oh, we have a problem. You know the old rule, which is it works better when you switch it on. But I think at this early in the talk, you might have been able to hear me anyway. But anyway, so now we have a microphone and we can go on. C++ serves a community of about 4.5 million developers based on the best surveys I have seen. I hear other people quoting larger numbers, but I haven't seen them verified. What does seem to be the case is that the C++ community grows by about 100,000 developers a year. So that's quite significant. So if you look at the usual lousy statistics on the web, I have to remember that we can't grow that much in percentage, because growing 4.5 million developers by double-digit percentages is really quite hard. It's all over the place worldwide and in different industries. One of the things about C++, it is far more used and far more prominent in industry than it is in education and research, and that leads some people to underestimate it. So I'll talk a little bit about that. And you can explain C++ in basically 2 lines. That comes from the original idea of what I wanted to do with C++. I wanted to have a direct map to hardware. I wanted to manipulate hardware. I wanted to write things like memory managers and process schedulers and device drivers. And for that, you need to be good at manipulating hardware. And C was pretty good at that, so I built it based on C, and also because my C support was superb. I had Brian Kernighan and Dennis Ritchie down the hall. So that was good. And this carries on. We're working on better support for caches, multi-cores, GPUs, FPGAs, SIMD, that kind of stuff. This is a core area for C++, and this is where quite a few languages don't operate, and so it is C++'s core domain. On the other hand, writing software for working really close to the hardware is not very pleasant, and it is not very productive. So you need to get away from the hardware, and for that reason, we've been working on abstraction. And everybody likes abstraction, it seems, except for people who want performance. And for that, you need abstraction that doesn't cost you anything. So I want something that uses a higher level abstraction to run as fast or faster than your hand-coded C or assembler. And we don't always succeed at that, but we do succeed so often that it's not just as good as, say, C, it is as good or better. Quite often, especially using higher level optimizations and compile time evaluation, we can actually beat what you think of as hand coding. And this started out based on Simula originally, with classes and inheritance, but also now there's templates for generic programming and such. And in the future, I'm aiming at complete type and resource safety, and I'll get back to that. But basically, we're close. There are tools out there that can be used to guarantee that the traditional sort of buffer overflows and dangling pointers and memory corruption simply doesn't happen by guarantees. So I'm talking about a modern C++, not how you write assembly code using C++, which you can do that too. And so the basic model for C++, I had to sum it up for a history of programming languages paper that I wrote for the conference that was supposed to happen this June, but it didn't, unfortunately. It would have been a really good conference, but I can recommend that paper. If you want to know what modern C++ is, that paper, which is really a monograph, that paper, that really is a monograph. It's 160 pages. It's a lot of pages, but not as many as they needed for JavaScript. So anyway, it's a very good paper for summarizing what is in modern C++ and why. But anyway, I had to summarize the C++ model of doing things. And basically, there's a static type system with equal support for built-in and user-defined types. It doesn't matter whether Dennis invented the type, or I did, or you do tomorrow. You can use them roughly similarly with the same kind of support in the language. We support value and reference semantics, which is a course of some complexity, but also the way you can build higher abstractions without losing performance. Systematic and general resource management. I don't want to lose any resource, like a socket or a other communication channel. Support for object-oriented programming in the classical style. Support for generic programming. And efficient is the word in both of them. It's not good enough to abstract. You have to be able to afford to use those abstractions. We do a lot of compile time programming these days. And then again, direct use of the machine and operating system resources, that's essential. It started out for systems programming, that's still a core domain. And then a lot of concurrency support, which is usually in the form of libraries as opposed to language features. That allows us to support a variety of concurrency mechanisms, quite often to get the performance and get the flexibility, get all the facilities of the hardware. You then need intrinsics, but then we build in those intrinsics. It's a long discussion about whether you want language support or library support for concurrency. I'm on the library side, but I'm also a fan of intrinsics to get things to work fast. So basically, when I talk about resource management, I talk about something very simple. Here, I'm defining a vector, a user-defined type. A user-defined type is known as a class. Anybody who calls a user-defined type a class can thank Christian Nygaard and Johan Dahl, because that's where that comes from. And we're trying to lift the abstraction level from a pointer and a number that says roughly how many elements there are there that the pointer points to a level where you actually have a vector that knows how many elements there are, that you can extend and contract and have operations on. So basically here, so we have the user-defined type, and it has two operations that are key to its function. A constructor that says if you want a vector, you have to give them some elements. And a destructor that says when you're finished, clean up the mess using that function. So it's a constructor and a destructor. And so here down here, we have a vector of doubles with some well-known constants, a vector of strings with some well-known language designers. Notice that the vector is a template. It's a parameterized type, and it has an element type. And you can combine these things more or less arbitrary as long as it makes sense. So here we have a vector, a pair of strings and J threads. There's threads that that follow this kind of model of how you write them, and you can initialize it with an initializer list. The important thing here is that you can build them, you can use them, and at the end of the scope, right there, everything's cleaned up. So the thread is joined, the string has its memory released, etc. All of that kind of stuff is done locally. There was a competition a few years ago about people had to mention their favorite C++ feature, and a guy called Orr pointed to this and says, my favorite feature is the end curly. That's where all the magic happens. So basically, if you understand what the end of scope is, you understand most of C++. This example here, except for the instantiations, was put in place in the first 2 weeks of the design of C++ constructors and destructors. During the first year, I was wondering about generic programming, couldn't solve it at the time, came later. So I seem to have lost contact. Try again, no. Backwards, forward. Oops. Let's see, try again. Okay, I will refrain from guessing which language this software was written in. Anyway, so basically trying to evolve C++ over the years, I knew very well from day one I couldn't build the ideal language, not even for me. So you had to work in a reasonable way by building something that you knew worked, see how it worked, see what was missing, rely on feedback, build it further. And I had some ideas like the good static type system and lack of leaks and such, but it would take decades before we got there. So it's a principled but pragmatic approach, and it's a process that's guided by feedback. And a lot of the work has to do with trade-offs. There you see sort of the kind of trade-offs that you do when you build aeroplanes. And if you look at research papers, quite often they show how to build sort of the lightest aeroplane, or the fastest aeroplane, or something like that. When it comes to language design, that's not what most people want. They want a good all-around workhorse. And so you have to do the trade-offs rather than trying to be the best at one or two things. You have to be good enough at everything and actually very good at a few things, preferably many things. And basically design decisions have consequences. This is something that determines what kind of applications you can do well, what kind of applications can you afford. If you make a design decision that requires gigabytes of memory, you are not going to work very well programming wristwatches or coffee machines. And so these kind of trade-offs are important. And basically, when you are evolving a language over time, and we've been evolving C++ over something like 40 years, there is two things that are important: evolution and stability. You need to evolve, you need to improve constantly to become better, to become more relevant, to pick up new learning, new ideas, to build basically simpler, safer, and faster code. On the other hand, the stability is important. The old code must run. And I get again and again the same request. C++ is too complicated, let's simplify it. Okay, I agree, it's too complicated. Now, but you have to add these two features. And by the way, whatever you do, don't break my code. I've got 1 billion lines of code, don't break them. Okay, so you can evolve, but you must not break the old code. And somehow we then have to make sure that people don't keep using the old features in the way that breaks all the good stuff that we're putting in there. So basically, I'm suggesting that you look at C++ and you use C++ as a modern language. Type safe, resource safe, and modular. And I'll get into that more. So basically, there was a story I told. And therefore, I am working partly on evolving the language to allow you to write better code, and partly on a set of guidelines and checkers for those guidelines that helps you move to the newer and better ways of doing things to get safer, easier to write, and faster code. And one way of handling complexity there is what I call the onion principle. You try to make simple things simple. And complicated things you can still do, but that might take some more work. And so basically what you think about is a set of layers of abstraction. Even that simple vector I showed you up before shows an onion. There's the vector itself, and down underneath it is the direct use of hardware through pointers and integers. And the reason it's called the onion principle is that each time you peel a layer, you cry more. You get more work, you get more errors. So don't peel when you don't have to. This is what I want. And this is what I'm working on in terms of the C++ core guidelines. You can write, type, and resource save C++. No leaks, no memory corruption, no garbage collector, no limitations on what you can express, and no performance degradation. This is C++ after all, not some new subset. And I want it to be ISO C++ because I don't want to design another language. It's a lot of work. I'm saying that it's a lot of manual labor. Make a successful language and you get 10 or 20 years to work on the manual. And I wanted two tools enforced. It is not really there yet. There's a lot of good stuff over on the Microsoft side in Visual Studio, a little bit in Clang Tidy. I really would like to have checkers universally available so that these kind of features could be widely available. Once you have these and have the checkers, you still have the problem of getting from the current old code to the more modern code. And we need to get static analysis to show you where the problems are. And eventually we'll have to do some more work, some more research in code transformation so that we don't have to do all of that by hand, because most people who can clean up 30-year-old cruddy code that happens to work but is hard to maintain, anybody who can do that probably would like to do something else. We need tools for that. So basically, C++ is controlled by a committee, an ISO standards committee, and that happened because sometime in 1989, representatives from IBM and Sun and HP, at the time the biggest manufacturers of computers and runners of computing, turned up in my office and said, "Bjarne, you want to standardize C++ under ISO rules." And I said, "But I can't, it's not finished, I'm not ready, I need more time." And they kept saying, "Well, you know, you really want to do this. Otherwise, we will do it, and you will not like the result." Oh yeah, and of course we trust you, but you can't trust your employer because we might be in competition with your employer. We need a forum that's open and everybody can be there. And of course you might get run over by a bus, so please. So anyway, we started. I wasn't too happy about it, but it was all right. And the committee started back when the world was black and white, and it grew and it grew and it grew and it grew. And you can now see the problem of evolving a popular language. There is about 250 people in that picture, and there are definitely 100 or 200 more that takes part in the process. And how do you get such a group of people to agree on anything? This is hard. This is hard work. I could give many other talks about that, but don't think it's easy. There's a lot of energy here. There's a lot of good ideas, and doing this kind of setting direction and doing the trade-offs is really, really hard. But so far we've succeeded. In February in Prague, we voted the next standard out, C++ 20, and it has some really major features: modules, concepts, coroutines. and some support for compile time programming. This is the main part of the rest of my talk. So I'm not going to go into details here, they're just buzzwords. But basically by major, I mean to change this the way we think about programs, the way we organize our programs, the way we, it's an attempt to improve our thinking. And this is supported by major standard library components, ranges, dates, formatting, parallel algorithms, and low-level access that are safe. And basically, there's also lots of minor features, and I fear minor features because that's extra complexity. Unless they fit in with something else, things get more confusing. But I will claim that C++20 has a dense web of interrelated and mutually supporting features, so that actually it's easier to write code in C++20 than it was in C++17, C++14, C++11, and C++98. Simple things have become simpler. More complicated things have not been made impossible. They've often been made simpler, and you can do things that couldn't be done before with efficiencies that couldn't be done before. So this is a good thing. C++20 is simply a better match for my original ideals than any of the previous versions. And so yes, it's too big, too complicated, etc. But if you use it right, you get a lot out of it. And so this is not science fiction. I mean, I love science fiction. I was so happy when I found that Douglas Adams were writing his early video games in C++. So if you've been writing Hitchhiker's Guide to the Galaxy or Dick Gently's Holistic Detective Agency and wondering what these guys were programming, we now know. Anyway, so I love science fiction, but this is not science fiction. The implementations are improving fast. You have to keep up with the latest compilers and checkers and such. And most of the features that I'm talking about today, most of the features that you find about C++ on the web are there. Not in all the compilers, which is sad. I like to write code that works on all the major platforms. It is not there. My guess is it'll be there certainly by the next GCC release. So somewhere in April next year, we'll be there with a fairly high proportion chance of guarantee. So basically, the modules are experimental in GCC, ships with Clang and Microsoft. Concepts are shipping everywhere now. Coroutines, they're still experimental in GCC, but I've talked to the guy implementing them. They're very close. And the library things are either shipping or available on GitHub. So, so much for science fiction. And so one of the aims, long-term aims, you can read a book I wrote in '94, The Design and Evolution of C++, is to make the preprocessor redundant. I really don't like the preprocessor. I don't want to write sharp define. I don't want to write sharp includes. I don't want if-indifs. I don't want assertions. I don't want to use macros just to get the line numbers. And we can get rid of all of that. The templates with concepts takes care of a lot of the defines, type deductions. It makes it easy to use. There's a lot of compile time computation so that you don't have to resort to macros. Modules takes care of the includes. Source location is the standard thing that comes in C++20, so you don't have to write underscore, underscore, file, underscore, underscore. Which is about the last macro I was using. Contracts should have been there, but they became controversial. So they're not there yet. And so you still need to use asserts or your local homebrew for asserts. I actually have a compile time version of something that's like asserts, so I don't use it anymore, but it's not standard. So when I'm talking about evolving a language, this is not small things. You've never seen a C or C++ program that wasn't littered with all of this stuff. But I was presenting to the CPPCon two weeks ago, close to optimal messaging system for taking objects, values of types, putting them into a byte buffer and shipping the byte buffer over. There's no macros, not one. Okay, so it can be done. Let me talk about compile time computation for a little bit. Using examples from the Chrono library, which is the standard library. It's done by it's done by Howard Hinand here. And basically, you can compose dates and times and things like that. But there I am looking, I want to know the weekday of June 21, 2016. And then I want to write it out. That's actually good standard C++, and it's very efficient. It boils down to just a couple of instructions. This is because it's done at compile time. So I can do a static assert, compile time check, that weekday is a Tuesday. And it will actually boil down to a runtime evaluation. No runtime evaluation. It's all done at compile time. So when I'm talking about compile time evaluation, I'm not talking just by integers and floating point numbers. I'm actually talking about user-defined types of a sufficient complexity to actually do normal dates in the ISO format and things like that. And I was trying something else. This is an example I borrowed from Howard. I want to check that in the year 2020, February, the last Tuesday, is that really February the 25th of 2020? The answer is yes. And the compiler can figure this one out quite simply. And the rest of Chrono has to do with things like time and time zones. So I can give me the time now. I can write it out, and I get this standard output formatted thing for what now is. So obviously I ran this on last year in, that's November the 14th at a given time. But I can also say, give me that time in the current time zone, wherever it is. So I was in Europe at the time. As a matter of fact, I was in Prague. And so it converts the time to the zone time, for a time zone. By default, you get the system time, or you can get the Greenwich Mean Time. Okay, that's again showing what can be done, and you don't actually have to do it. You can go and download the standard library. Well, actually it comes automatically downloaded, and just use it. And here I'm showing how to do the unit system. So here I want to have the square root of 3 plus 2.7 imaginary. So that makes a complex number, and then it calls the complex square root, and we get that z to be complex. Or I can do some time calculation. That's very popular, 5 minutes, 10 seconds, 200 microseconds, and 300 nanoseconds. If you're doing low-level stuff where timing matters, this kind of stuff is really nice. Try and do that in most other languages, and it gets very complicated and very error-prone. These kinds of calculations are often wrong when done by people and put in as constants. And here we have to live with the C style of character strings, which is the literals here, but we can put a suffix on and says make this a C++ standard string. And the code for doing that uses what's called literal operators. So there is what happens to a suffix I. It takes a double with a suffix I and returns it as an imaginary constant for a couple of complex of double. If you have a subscript S to an integer, you get a result. If you have a subscript S on a standard literal, string literal, it returns a string. And this is all done at compile time. This is what those const expr things do. So this is straight code. The implementation is of everything here is 3 lines, and the compiler calculates it very fast. Well, when we first invented this, I was a bit worried that it would slow down compilations, but it didn't. I haven't been able to measure it. This is pretty good. And if you want to do any of this kind of stuff here by hand, compiling that by hand stuff is also takes time, probably more than this stuff here. And a lot of this relies on template argument deduction. So if you want to do elegant code and you want to do very expressive type systems, and if you want to do things at compile time, you need to reduce a lot of notation so that you don't actually get very verbose. So here is a new type. Here's a new type, span, which is in the standard. It came from the guideline support library, where we invented it for the support for the guidelines. Because we needed something. People play with low-level code. They play with arrays, sometimes on the stack, and they want to have type-safe stuff there. And a span defines a range with a beginning and an end, and it allows you to do things like that range for loop for all x in S, write them out. Since it's a span, it knows where the beginning and the end is, so it can do the output. If you go on subscript, it'll do range checking for you, so you don't fall over the edge. Don't use raw pointers and raw integers, use a span. So if today I was going to write that vector class, I might actually use a span rather than the even lower facility of pointer, comma, integer. The span holds that. Furthermore, notice that I didn't say that the span was a span of integers. After all, I gave it an initializer, which was an array of integers, and it looks at that and says, well, it's a span of integers, and there's 128 of them. So we can get rid of a lot of repetition that way. Another example here is the logs here. This is the way we avoid some what's it called, deadlocks. I want to grab 2 mutexes, and mutexes come in a variety of flavors. And so this here deduces what kind of logs they are from their declarations, make a log object that keeps track of it, grabs both on either, and carry on. But the point is, I don't have to know what kind of mutexes those are. Type deduction, that's a key thing here. And now one thing I should point out, and I'm trying to point out, is these things are done by people. Languages are not sort of coming right out of some deductive process and such. Maybe it is, but it's done by people. And so here are some of the people that has worked on the compile time computation. I think it's a major and important part of modern C++, and people don't usually talk about it because it's a lot of little features that work together. Me and Gabby Does Raise did the original constant compile time evaluation of functions back around 2010, and everybody assured us that they were not only impossible to do, they were also useless. They are all over the place now, and there's more support. They are the key to a lot of what we saw here, the user-defined suffixes and unit systems, you name it. All of the rest is based on the fact that we can compute any pure function at compile time. Very important thing here. And now I think I have met my target, which was to give you 5 minutes to ask questions about this part of the talk. And then I can have a quarter of an hour break, and then we'll go further into many more technical details. So if you ask questions specifically about some of the things that come later, I'll just say later. But if you have questions on this section of the talk, this is a good time to do it. Yeah.
If you could go back to slide 20.
Slide 20.
About the new time, the date, specifically the year. Here, when we calculate auto D, say we have.
Is it this one? Or?
Yes, this one. The second line, you have 5 minutes plus 10 seconds and so on.
Yeah.
Say if we had 1 year as one of these components.
Yeah.
How would that fit? Because a year depends on which year.
Yes.
This is something I've actually a problem.
I am not sure whether we have a year constant for that reason. Okay. What you can do is you can name a year, but I don't actually remember if the standard supports that. And the problem that not all years have the same number of days and such. Yeah, I don't know how it's handled. I know this stuff here handles multiple years. It handles things like what was the daylight saving times in New York in 1944. So you have to have the year and the location. The answer is you're 3 hours off. It's one of Howard's key things. Furthermore, this stuff handles leap seconds. It's fairly thorough. It's a beautiful library. And so if there is a question like that, if there is a good answer, I'm pretty sure it's there. And if there isn't a good answer, Howard would not have given you the facility.
Right.
And there's some really good talks on CPPCon on this by Howard Hinand. In general, there's a lot of good talks about C++ on YouTube. Some years ago, we started with CPPCon. And the C++ Foundation that I was part of creating arranged that all of the talks are professionally recorded and put on the web immediately. So you can now get all of the talks from C++ 20, CPPCon 20 on YouTube now, and that's 2 weeks after it finished. And so that's a good source. But if you want to know these things, look at the talks by Howard Hinand. He may have the answer. If he doesn't, send him an email.
Yeah, there was a question from the online audience.
Yeah.
Someone asked, with modules, do you expect to remove header files completely for implementations not using templates?
Later. This is the first thing I'm going to talk about after the break. Yeah.
You touched a bit on it in the startup. There's all these things happening now that makes it easier and better to use C++. But as you said, it's not being taught as much as it's being used. What is that a problem that should be handled, or is that just the state of things?
C++ was always used significantly more than it was taught. And with all due respect, quite often the teachers taught it very poorly. There are still many teachers that teach C++ as this was 1988 or thereabouts. And this is a major problem for C++, for C++'s reputation and for C++'s users. There are people that are taught C++ in ways that I think is child abuse. I mean, the way what they are taught is to how to write really poor code that they'll have a hard time debugging and they'll have problems. Okay, it's a major problem. It started really in the early years where we couldn't teach teachers fast enough, and that is still the problem. And a lot of people giving talks tries to make it really complicated. They don't show the one-liners that I like to show. They show many places. There's very little that anybody can do except give good examples. So I write some books. There's a study group in the standards committee that's trying to give some guidelines for teaching. I actually use the C++ core guidelines as a teaching tool, and that was partly written based on my teaching. By the way, the C++ core guidelines is an open source project by many people. Noticeably, well, there's Morgan Stanley, of course, Microsoft, Red Hat. There's lots of people from places like Google and some academics. So it's a good project. That's a good place to look. If you are teaching something that would violate the core guidelines, you're probably doing something wrong. It doesn't say how you teach this, or even how much you teach it, and certainly not in which order you teach things, which is one of the things that the study group is trying to help with. But it does give you some guidelines about why, what can be taught well and what has worked in the past. Well, yeah, big problem. Also, a lot of organizations like to teach fancy advanced stuff and think that programming is something anybody can pick up if they're smart enough. And they are not picking this stuff up if all they've been taught was, say, Java, or for that matter, Haskell. This is different.
There's another question from the online audience. It says that backwards compatibility is nice, but why not do a new C++ from scratch without considering backward compatibility? Would the result be a similar language, perhaps more efficient, but with a much simpler syntax?
That's an interesting question. Sometimes I see this as a time machine question. That is, if you knew what you know now, what would you have done? But the answer is that getting a new language designed is not actually that difficult. Implementing it is not all that difficult. Matching the tool chains and the support and the teaching and the libraries on top of it is very, very hard. And talking people into using something new is very hard. So one reason I want to maintain compatibility is really, I can't leave that 4.5 million people in the lurch. They need support, they deserve support. I'm not doing this for my own gratification and for sort of research. This is a language for use. And you use a language when you are confident that it can last for 10 years or so, or 20. That is, if you are an organization, your time scale is different. If you're building a student program or a little thing for yourself, you can use a new language every second month. But if you are an organization and you want to write, say, the stuff for controlling sort of wind turbines or ships or telecommunications software or banking software, you can't afford to rewrite it every decade. Or maybe you can afford it every decade, but not much short. Yeah, he agrees with me. But certainly not much shorter than that. And therefore, you need a language that can last. One of the things that C and C++ has demonstrated is that you can actually be viable over decades. And I'm not going to mess with that. To prove that with a new language, it's not just the syntax, but you have to prove that it will last, that it has a community that will support it. And this is interesting for C++ because we've never had a rich owner. We've never had somebody whose business it was to maintain it. It's always been that my company relies on this, so we better have an implementation. And this is how we have the major implementations now. All of those things are very important. And I guess I don't want another decade of manual labor on something else, or 2 decades. That's just too much. Been there, done that, got the t-shirt. I really don't want to do that again. And then, yes, I think you could build a language that has the fundamental facilities and performance of C++ at about 1/10 of the size. It is not just syntax. It is also, you have to get the semantics more regular and get things to work together better. But it will be a major piece of work, multiple years, probably from multiple people, but you have to maintain the direction. You can't follow all fashions, and it will probably not work. That is, moving people from C++ to that would be really hard. This will work when we have the technology for code transformation that are close to perfect, but we don't. That's another decades of research. Maybe this is break time, and you can ask more questions later.
Yeah, I think we should take the break now.
Then we can start again. So I'm going to talk about modules, and the most obvious word about modules is finally. Welcome to the 21st century, or even to the 1990s. We started out with, in C++, with C's include mechanism, and that worked, and it actually sometimes worked better than people believe. I've seen module systems that had to be taken away because they didn't scale and gave to the way they should. But really, the preprocessor is cruddy. I wanted to get rid of it a long time ago, and I've been working slowly to get there. So the problem with include files are basically twofold. One is there's order dependence. So if you include A followed by including B, you can get a different results from including B and including A. And finally, include is textual inclusion. So what you end up with for including A and B is the text for A and B and everything that people use to express A and B. That implies that there's lots of repeated computation. You can't just compile what's in A and then compile what's in B, because when you use them in some other context, the meaning might be different. And there's lots of subtle bugs. So it's a lot of work, and it doesn't do too well. So we want modularity. Import A followed by import B is the same as import B followed by import A. Very simple. That means that you can actually partly compile A and B separately. This has been known for a very long time, but how do you get it into something when you have a few 100 billion lines of code? Again, the problem is, how do you get things deployed? What was that? It's done that before. No? Okay, I'm doing it, so maybe you shouldn't try also. There's a reason I often use my own my own computer. There. So basically, imports are not transitive. That is, if I import something, I don't implicitly export it to my users. And this implies that much of the compilation can be done once only, and it's done. And this has interesting effects here. That's the interesting effect. I borrowed this from somebody I've forgotten the name of. The other problem is this is probably the wrong version of the talk. This is why I'm confused. That one should have come right after, and there's a name. This is 25 times faster compiling using an include, using an import than using an include. So we're talking about major benefits here. That's what we're going after. And this comes from hygiene, from better writing, better code, basically. So here's an example of how to make a module. I say I want to export a map printer, and I want to import a few things, IO streams, my containers library, and I'm going to use the standard library. That's what the first lines do. Then I want to export the function print map. And that uses a lot of C++ 20 magic that we'll get to in a moment. Basically, it says that it should be a template that you can print the value types of. And then I can go and basically say, for all key value pairs in the data type map, which is a sequence of things that you can print them out. So that's just a very simple but interesting function. And that's all it takes to define a module. And this can then be stored away and used properly. And this was deliberately using fairly advanced features. When I first wrote this was in 16 or something like that, trying to encourage people to get C++ 17 done right. But now it is C++ 20, it works. And then you get this effect. Now the problem is, how do we get from here to there? When we have these huge code bases, millions, billions of lines of code that users include, how do we get there? Well, one of the first ways is that you can actually, there's something called the global module, where you can include all kind of old stuff. And so you could start up with all your include files there, building a module. Now the consumer of that module doesn't see all of that stuff. They only see what's exported. So that's the way you can grab everything unchanged and then export what you want out of it. So that means that you can have parts of your code where include works exactly as before. So you can take include file after include file and slowly modularize it. And then there's a facility which I happen to dislike, which says you can take any include file and import it. And what happens there is that it goes and checks that there are modularity, so that import A followed by import B is the same as import B followed by import A. So this is the way that you can start using your own file, the old header files, if they actually were good. And then you can absorb them into your module system. I think this is dangerous. I shouldn't call it a hack. I'll change that. But it's certainly dangerous because it'll encourage people not to clean up their action. It'll encourage people to use old header files and complain when they don't work and things like that. So I'm not too keen on that. But the point is, there's a lot of work that goes into making this work at scale in real code bases. And that work's going on now. And we have not yet been able to ship a modular standard library. That is, the standard library is defined in terms of header files. There are implementations where everything has been put into modules, but they haven't gone through the standards committee yet. So that'll happen. In particular, I want to import standard. Just give me it all. Since this is pre-compiled and you only look at what you actually look at, you can afford that. That I think this will be very interesting. And again, things are done by people. Nathan does the GCC implementation, Gabby does Race does the Microsoft implementation, and Richard Smith does the Clang implementation. The implementation at Microsoft by Gabby is based on a representation of C++, a little library, 3,000 lines for representing all of C++ that we did many years ago to enable representation of C++ for higher level stuff like this. So I've got a tiny little hand in this. This is good. And basically they work on source organization, they work on header file conversions in addition to the to the basic language facilities. And there's a huge discussion about how to get the build systems up to state with modules. They have had 40 years of optimizing the build systems for include files. And so people now want, in a couple of months, to beat 40 years of work. And it's not that simple. There are some papers, you can find them out on the web saying it's impossible. You can also find the paper where he apologized for saying so, because it worked. But build 2 can do a decent build here. And there's a CMake prototype that was done by Nathan in 2 weeks in his spare time. So if you hear it's impossible or it doesn't work, you're wrong. Furthermore, I should mention that Microsoft is working rather nicely. So it's coming. But a lot of the effort on modules is exactly on the things that has nothing much to do with language design. It has to do with how do you upgrade a code base? How do you provide support for that kind of upgrades? And now I'm going to talk about generic programming. That's the backbone of the C++ standard library. So people who have been taught that C++ is all about inheritance will get a little bit disappointed because there's very little inheritance in this. But it's all over the place: containers, ranges, algorithms. The concurrency support is all generic. Time, I showed you some of that from Chrono. Random numbers, the numeric types, even the strings, because you need strings of different character sets, and formatting. So basically, we have a system based on parameterized types and parameterized algorithms, a lot of type deduction to get this to work, and of course, resource acquisition is initialization. There's this weird name that I came up with for using constructors and destructors, probably. I was busy that year, so I didn't think of anything better. But basically, generic programming is basically to write code that works for any suitable argument. So I want to sort, and that definition of sort should be sufficient. I want to sort something where R can be any sequence of random access, and R's element should be compared to using less than. And I don't want to return a value. I mean, nothing is spelled VOID in C, because, well, in the old days, nothing meant int. So we can't have nothing meaning nothing. But anyway, this is sort of the pseudocode we would write. And for algorithms, we could say find if takes a range and a predicate, and then it returns something that finds in the sequence something that meets the predicate. And so our job in terms of language design is to figure out how to define R and P here so that this stuff works. And basically, that's what is done with concepts for C++ 20. It was done mainly by me and Gabby Dos Reyes about 10 years ago, and then it took some time to get it in. Actually, no, we had the drafts ready in 2005. But we have to make sure that definitions of R and P can be given to the compiler. So this is the way the code really looks today. I can say I want to sort a sortable range, and it's passed by reference. And now if I have, if I have a vector of strings, I can sort it, and it'll go and say, is vector of string a sortable range? Is it a range? Yeah. Does it have random access? Yeah. Is the element type something that I can compare with less than? Yeah. So I can do it. And here I can also try an array of 128 integers, and it asks the same question, and the answer is yes again. And so a concept specifies what's required of the type of the element. And the thing here comes in when I was talking about type deduction. It's implicit what the type of the container is, what the type of the elements are, the number of elements, and the comparison criteria. Because the compiler already knows that, so I don't have to tell it again. That's useful. And the definition looks sort of like that. There's the find if. It comes as part of the standard in the ranges library, so you don't actually have to define it, though the definition is 3 lines of code, so it's not too bad, but it didn't fit on the slide. So basically it says it has an input range. Input range is defined in the standard. I don't have to do it anymore. And the marvelous name, indirect unary predicate. So basically it says a predicate has to call through a pointer into something, and then it's a unary predicate that's called on what you find. And then it returns an iterator. This is cryptic, but it's also standard, so you can look it up, find the definitions and use it. And anyway, most of the time you don't have to look at it, you just use it. So I have a list of an integer, a list of integers here, and I say find if the list of integers and greater than 7. That creates a function object that compares to 7. And so basically it says, is the list an input range? Yeah, it's a range you can traverse from one end to the other. And is greater than a predicate that you can apply to things you get out of that range. Yeah, they're integers and it compares to an integer. It'll work. The compiler can figure this out. And if you don't want to define your function objects and give them names, you can use lambdas, which basically here I'm finding find if I'm finding something in a vector of strings, and I do that by comparing the elements of the string with that function there. And what I'm doing there is I'm checking whether they've got vowels in them. And again, I can write the function has vowels. You don't have to be a genius to do that. So it sort of works, and there's library support for it. What is missing for modules just now is a library support, but it's in place for generic programming. And you can handle overloading. Now, the standard says that you can only sort things that has random access, sequences with random access. So what if I want to sort a list? A list doesn't have random access. You have to work your way through the list to find another element. And so I can say, well, I can just define something that defined what a forward sort of a range is. It's one that doesn't require random access, and I can sort one of those. There is actually a pretty good algorithm for doing so. You can read it up in Alex Stefanov's writings. However, my favorite is very simple. I take the list, copy the elements into a vector, sort them, and copy them back again. Again, the code of this is sort of happens to be a lot of 3-liners. Having done that, I can now say I have 2 sort functions, one that wants forward and one that wants just the random access, and I can call them. If I call it for list, it must call the one that's forward sortable because it can't call the other one. It doesn't have random access. And if I have a vector, I have a choice. I can pick the one that doesn't require random access or the one that requires random access. Now, the way this is resolved by the compiler, not the programmer. It says, well, one of them is strictly more restrictive, strictly better than the other. So we pick that one. So if the set of predicates that you're comparing happens to be subsets, you can resolve it. If they're not subsets but overlaps, you can't. And if they're disjoint, you don't have a problem because you only get one of them. That's the overload rules for concepts. Essentially complete. And so I use the word predicate. Concepts are simply predicates, compile time evaluated predicates. First order predicate logic. We have the const expr functions that really grew into concepts. So a concept is basically a compile time function that you can apply to a type or a value to get the answer yes or no. That's all there is. Are you an iterator? Are you a range? Are you a range with random access? Are you a predicate? And if so, is it the kind of type that you are a predicate of? That kind of questions. It's exactly the way we talk about them. And so here's an example of a definition. I use sortable range. This is not in the standard, so I capitalize it. So it says the concept sortable range, and R is a sortable range if it is a random access range and its iterator is sortable, that you can sort iterators. Fine. And a forward sortable range is if it's a forward sortable range and the iterators are sortable. An iterator is sortable if it points to something you can compare and you can swap. That's a definition in the standard. Again, this slide is complete. It just uses the standard library to do it. Sometimes, however, you have to go down and actually mess with the language itself rather than just the standard library. And here is how I define equality comparable. What does it take to compare two things? And basically it says you can compare a T and a U if you can compare a T and a U with equals, with not equals, and if you can swap them around. It's a symmetric operation if you can compare a U with a T and with equals and not equals. And by the way, this is a binary operation because comparisons tend to be. I want to be able to compare C-style strings with C++ style strings. I want to be able to compare integers to floating point numbers and things like that. But I default right there, I default U to T. So if you only give me one type, it'll work. And that's for numeric. That's for, yeah, that's the way that's done. And that equality comparable is in the standard library, so you don't have to write it. But again, so it's not as complicated as some people make it. Now, types and concepts are very related things. So if you think about it, what is a type? A type is something that specifies a set of operations that can be applied to an object, implicitly or explicitly. And it relies on the language, function declarations and language rules to do that. And in addition to showing how an object can be used, it specifies how an object is laid out in memory. That's the way you have a type. A single argument concept is very similar. It specifies which set of operations that can be applied to an object, directly or indirectly, and it relies on use patterns at the lowest level, and then you build up to more concepts. And it says absolutely nothing about the layout of an object. This means that we can actually do whatever we do with type checking, we can do with concept checking, except when we want to know what the layout is. That has to come from somewhere else. So my idea is that essentially all code becomes generic, specified with concepts, and you only need the layout when you create the initial object. That's the idea. So basically, generic programming is just programming, and well, basically programming is just generic programming, because when we look at it, when we say plus, we don't usually think about whether it was an integer plus or a floating point plus or a complex plus or a complex and a floating point plus and all of these combinations. It just sort of falls out of this. And so I've been worried that template programming and template metaprogramming has become a dark art that people has to learn a lot of new things. There's different syntax, different lookup rules in the language, different source code optimizations. It's really expert friendly. This is the kind of stuff you can give conference talks on and impress your friends and piss off your users. So basically, I don't think we need two different sets of techniques and notations. What we learned when we started writing simple functions like find something, compare something, do a square function or something like that. All of that recycles. It looks the same, except that we now use concepts instead of types. And so simple things become simple. And ordinary programming is expressive and familiar, and we can use that for generic programming again. This is conjecture. Of course, I have not proven this at scale. I proved it in fairly large programs, but I haven't got million line code bases, billion line code bases that prove this point. So this is a claim, it's a conjecture, but I think it's a good one. And the work on this was done to a very large extent by those 4 people. That is Alex Stefanov that came up with a lot of the fundamental ideas here, together with Gabby, and I worked out most of the language stuff to go with it. And Andrew Sutton here implemented the first compiler that did it. He modified GCC to do it. At the time where a lot of this work was done, I was at Texas A&M together with Gabby and Andrew. They were my postdocs to start out with, and Gabby got to be a professor there. But now we left. A lot of the work was done there in the north or so whatever, 2007 plus minus a bit. And then I'm going to change gears again and look a little bit about concurrency. We have concurrency and parallelism supported in C++. And basically, we want to simplify programming. If you've written sort of POSIX style C code, you know what I mean. This is the pain. Lots of void stars and things like that, macros and such. We want to have type system control and to help us. And we want the performance to be optimal, because why else would you mess with this level of programming with concurrency? I mean, if a single thread will do things fast enough and cheap enough, do that. So we need to maintain it. Portability across different forms of hardware is really good. We're working a lot about code that can work both on CPUs and GPUs these days. Good stuff. I want FPGA interfaces to be nicely typed C++ rather than messing around with definition languages and such. And we want system level interoperability, because whatever we do, we have to be able to talk to the system. Operating system talks a certain language. Code using that operating system will use the module supported by that operating system. So we can't just go and define the ideal concurrency support system. We can do that, but there also have to be the mapping to what's existing in hardware and systems. Okay, so C++ 11 provided a traditional foundation. We formalized the memory model for C++. This is interesting. Java had a good one, so we tried to adopt it, and it got vetoed by people like Intel and IBM, because if we adopted the Java memory model, their Java virtual machines would slow down by at least a factor of 2. So we had to do something somewhat more clever and quite a bit more complicated. Now, the result was that Java ran nice and fast, and C++ was criticized for being too complicated again. But that's still life. We helped a major set of applications, so that's good. And then it provided block-free programming. That's for people who think juggling naked saws are too not challenging enough. And then provided a type-safe version of the POSIX Windows style with threads, mutex and such. Basically take what people have all the time, but make sure they don't have to use all those macros and all of those untyped facilities. Provided future and promise facilities and atomics. I'll get into that a little bit later. And again, C++ grows incrementally, but with some direction to it. C++ 14, 17, and 20 provides as many minor supports. There's a bug there. The SIMD support was dropped in the last minute and postponed to 23, but it exists. You can get it. And C++ 23, we're working on a general model of concurrency, an asynchrony that can do both push and pull operations. And then we'll finally get a networking library provided in the standard. So a thread represents a system's notion of an executing task. And you can start a task on a thread. A thread can wait. You can wait for a thread for a given time. You can access data through mutual exclusion, control access through locks. You can have condition variables, etc. And you can read with the future. Or everything but the future is very standard for anybody who's written operating systems. It's just a better way of saying it. So this is a foundation that we absolutely had to have. No choice. And so we did it. It's, I think that the threads and lock model of concurrency is about the worst model there is for writing applications, but this is the way the system is. This is the way the world is. We have to do it. So let's show some of the things that actually work. So I mentioned unlocking deadlocks before, just using RAII again. So basically we have something shared, controlled by a mutex. We have something else shared with a mutex, maybe a different kind of mutex. It may be in a different part of the program. And we can grab the lock, grab both locks. We don't get fast here till we have both. And we back off if we can't get, if we get one and not the other. So we don't get the deadlock, so manipulate the data and then we release both locks. So again, there's some fairly simple thing. Try to do that in raw POSIX. It's actually quite complicated. Of course, it can be done because we did it. It's just hidden there, a good algorithm for doing it. We have reader-writer locks now in, I think, since 17. Basically, a writer needs unique access, so it grabs a unique lock. Readers are willing to share with other readers, so they grab a shared lock. Takes care of a fairly large set of applications, not all applications, but again, we're sort of nibbling off the application areas. If this takes 90% of the reader writers, we've done a good job, and the last 10% you have to get clever again. One thing that was missing earlier that we get in C++ 20 is, what if you've got a bunch of threads and then you get tired of them and want to kill them off? A typical example of that would be start a parallel search. Start maybe 100 threads looking in different parts of the space. And when you find something, you're done, you've got it. It's a find one, not find all. What do you do with the other 99 threads? You somehow have to kill them, but we couldn't get a cancellation feature in POSIX, so we had to do something else. And so this works here with something called a stop token. If you give a task, which is what you run on a thread, a stop token, it is obliged to ever so often look. And so most of these operations have a main loop in them. So you just stick a test on of the stop token in the main loop. And so once they are not needed anymore, the user set the request stop. In other words, please go and kill yourself. And the 99 threads, each time they get to the top of the loop, says, oh, I'm not needed anymore. Boom. And so this is very simple. There's nothing novel in it. I think I did things like that 30, 40 years ago. But the point is, it's now a standard for it. And it's quite simple. And all the synchronization and difficulty of doing this is taken care of, because anything that involves concurrency is potentially subject to data races, and that has been taken care of. Future promise was something we put into C++ 11. basically you have a result that you want to pass from one thread to another. And the idea is you give the thread that produces the value what's called a promise, and it can set the value or it can set an exception in it. If I want to get it, the result, I get the future, I read it. If it's not there, I wait implicitly. If it is there, I get it. If an exception was set, an exception is thrown, taken care of. The important thing is I can now write code without any explicit locks. And this can be optimized. So we have a model where we can say, run these tasks and wait for the results. This is being improved again. Future and promise is a terminology from Interlist back in the 70s. This is why it doesn't look very C++, sound very C++ like, but it's a good old idea of a buffer for exchanging things. I would have liked to have many results so I would get a pipeline of them, but I couldn't get it through the standards committee. So here's the way code looks. A user simply looks like that, get the result. And a producer says, try doing the work. And if I succeeded doing the work, set the value. If something wrong happens, you get an exception. You set the exception so that an exception is thrown when the get happens. This is sort of the simplest possible communication mechanism. And again, you don't see any logging here because that's become implicit and fairly easy to do. This has to be improved also. We would like to be able to have a callback rather than an explicit get. That exists but hasn't been standardized yet. We have a model in standardization of shipping things when it's ready, as opposed to waiting till all the features are there. That works. The other thing we got was coroutines. Now, we wouldn't be here if coroutines hadn't been in the initial C++. I wrote a coroutine library that was my bread and butter for about 10 years. But the guys at Sun couldn't implement it easily on Spark, so they didn't ship it, and that meant that nobody could depend on the coroutines, and so they disappeared. But we've got them back again. Anybody who know coroutines will know they are good. Anybody that doesn't, think of fast pipelines and generators. They get really nice with this. And so basically, a coroutine is a function that can save its state in between calls. So basically, it keeps the stack frame around so that you start up again where you ended. So the way this code works is that this is Fibonacci series. So you have some initial values, and forever you get the next element, which is the sum of the previous one, and you return it. Once you get started at the next call, you make the next two elements what they are. And so it generates 0, 1, 1, 2, 3, 5, 8, 13, as it was. This is sort of not a very fantastic example of coroutines, but it fits on a slide. And that's valuable. It shows the mechanism for doing it. And all there is to it is to be able to save that stack frame. Now, since people want hundreds and thousands of coroutines, it is really important that this is efficient and that the stack frames are not larger than they should be. There's lots of debates about this, but yes, people do this for hundreds of thousands of coroutines in a program. Saves a lot of threading because threading is very much more expensive than this. Some of this stuff can be done at compile time. I've actually seen a generator that generates things like that, do the first 10, and the optimizer took a look at it and went much in an output sequence without any function calls. So it is not whether we can do this, it's whether we can do this affordable for the task necessary. A less contrived example is they have been using things like this to compensate from the latency of accessing things in memory through the cache hierarchies. There's a paper about that. If you need to see it, send me an email. I've forgotten the link. But anyway, basically, we can now write for all V in Fibonacci, write them out. This loop goes and says next, 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 next. And each time it gets a new value and writes it out. Yeah, I spent a decade basically living off coroutines. The idea comes from Simula to me. It's an old idea, but I got it from Simula. These are not as general as Simula ones, but much faster. So here's another example. This is from asynchronous I/O using the Azure library. And basically it says there's a buffer and read something in it, wait for the result, then write it out and wait till you do next. And it keeps a state here. So you go around and around, reading a buffer at a time from the socket and writing it back out again. That is actually semi-real. We have a whole bunch of parallel algorithms. If I want to do concurrency, I would really, really like it if you did all the work. That is, if there was an algorithm where all the clever stuff with asynchrony and parallelism and load balancing and the works have been done by somebody else. And that is what the standard algorithms do. We can have sort from beginning or end of a sequence, or we can say try to parallelize it. Or you can say sort from the beginning and the end, but there are no dependencies there, so we can vectorize this thing. Unseq means unsequenced. And these are the standard ones. Unfortunately, the range version is not there. I would like par range and unseq range, of course, but it didn't make the standard, so I have to write them myself. They're not hard to write. It takes one line. It's so if I want the sort of parallel of begin and end, I will say sort of parallel of a range. The implementation of that is sort parallel the begin of the range and the end of the range. That's the implementation. But you have to do it yourself because it didn't make the standard yet. And there's the standard algorithms, and then there's a bunch of new ones, parallel accumulate, reduce scans, inclusive, exclusive, good kind of stuff. Most of this stuff is done by the national labs in the US. And we're not finished. C++ sort of evolves as it has to, and we have a plan. It was written out mostly by Ville Voutilainen, who works for Qt and is the Finnish representative of the Standards Committee. Basically, give us the proper library support for coroutines. What I showed you was a non-standard type task and generator. There's the generator. There's the task. They are not in the standard yet. You have to download a library to get it. We don't want that. We want it part of the standard library. A modular standard library, it's very important. I want to be able to say import all the containers, import all the algorithms, import everything. That's what I would like. That's on the plan. Executors is a general model of concurrency and parallelism. We want that. And once that comes, we get networking for free, basically. It's done, but we have to finish there. And then we are trying to make progress on static reflection, pattern matching, functional style pattern matching, and contracts. Contracts almost made it into C++ 20, but some controversy ended up at the end, so we could do it. And we have to be careful. I remind people a lot about the Vasa, which was built, and the king wanted a bigger and better battleship with double gun decks and more statues, and he got it. Rumor has it that the designer, shipbuilder, committed suicide in the process. They cheated with the testing. the way you test the ship like that is you have the crew running from one side to the other of the deck, and if you can do it 14 times, it'll survive in the North Sea. The rumor has it they stopped at 7. So everything was done wrong there because everybody wanted the greatest and the best as soon as possible. And C++ could get into real trouble if we don't have a plan, if we don't restrict ourselves to things that really works and we understand. So that's the plan. And we were well on our way to do it. I thought we would get most of this, but well, things happen. And the committee can't meet face to face, and that is very difficult. So don't be too impatient. Even the best plan can run into problems. The best plan that we could make is still there. That's the plan. But if we get one of these things, I think we should be happy, given the state of the world. And yeah, we ship a feature when it's ready and only when it's ready. That's the idea. So we ship modules without the module support library because the module support library wasn't ready yet. And we don't have any paid sort of secretariat to do work just because it's needed. Work is done when everybody agrees or if somebody actually does it. And for that reason, we have to be careful with scheduling and planning. And so here's a whole bunch of references because, well, I talked for an hour and a half and I can only say that much. I really recommend the History of Programming Languages paper, which is the last paper on the subject. And for many of the new things, it's also the only place where you can find what there is and why. And so that's it. And there's more stuff in places. And so basically we have C++ 20. It was technically finished February the 15th. Most places are shipping. We expect most features or all features be shipped by all the vendors in 2020. I don't think, I mean, for GCC modules are, I believe, on the trunk, but they are not shipping till next year. So we can get a discussion about whether it is shipping or not when you can get it, but it's not shipped by default. And this is going to make a huge difference to the way people write programs and think about programs. Some of the effects of this will take a decade to work out, but it is major. And C++ 20 is compatible and stable. We are getting better. We, the standards committee, are getting better at compatibility and stability. So it's easier to upgrade to 20 from 17. It was easier to upgrade from 17 from 14. It was easier to upgrade from 11 to 14. And it was living hell to upgrade from 98 to 11. We're getting better at this. And to get the benefit of C++, try writing modern C++. You can write C in it, and you get what you deserve. And you can write Java in it, and again, you'll find that you get a lot of class hierarchies and macros, and it doesn't actually run like modern C++. So use it as a modern language. And as I said, there's a two-pronged approach here. There's a language improvement, and then there's a guidelines to get people to encourage people to write more modern C++. It's just better, it's faster, it's safer, it's easier to write. And now I think I should switch to questions.
Any questions from the audience here?
So if we think about legacy code, 5-10 years old code that you may have around the company, that may be still running C++ 40 at most. In many companies we see that. How would you approach bringing this to modern C++?
The 14 is not so bad. The 98 is the interesting case. But basically, it's hard to give a sort of a general rule. And I think the hardest bit is actually non-technical again. It's to convince the bean counters that they should put some effort into avoiding the technical debt that they are building up. And my best argument is that modern C++ runs on modern C++ compilers, and they optimize much better than the old compilers. So by upgrading, you get the benefits of faster code, and you can use smaller server farms and things like that. Now, practically, I think what you need is to do it piecemeal, do it one feature at a time. And the way to do it is to have a tool that finds the stuff that you would like to upgrade. I did some experiments upgrading C-style for loops to range for loops, and so then to find parallel algorithms from that. And a lot of that can be automated. If you can prove that it can be transformed, do it. If you can't, this is where the human gets into the loop to see what can be done. And I think we need many more tools like that. The beginning of it can be done with Crank-Tidy and with especially with the Microsoft Visual Studio static checker, the core guideline checker. There is something called profiles, so you can say, find all the potential range errors. And it will not do anything for you, but they'll find them. And then you can go to the range errors and says, oh, he's doing silly things with pointers. Let's introduce some spans. Or, wow, that's a C-style for loop with range checking. With going to a range loop, you just make sure that the range exists and you don't have to do any more checking. But basically, use a tool to find the particular problem you want to attack first. Range checking is an example, dangling pointers is an example. We have some support for that approach. If you don't have a tool, you end up doing code reviews saying, well, try and find all the places where you might have a data race. You really should use a tool for that. But once you find them, you can then upgrade the code. Is there any deadlocks in my code? Remove all the explicit codes and use a scope lock. Is there any locks that are not unlocked? Which you write to things that lock, unlock. Change it to RAII and have the unlock implicit. So basically, pick the problem, try with the best tool support to find all occurrences of the problem, and then with as much help as you can get from code transformation or by doing it yourself by hand, do it.
We do have a couple of questions from.
Yes, so from the online audience, people thank you for a great talk. It says that it's a wonderful news, and thank you for the talk and the language.
Oh, thank you.
And we have two questions, and the first one was actually asked right before the break. He says that for him, the most anticipated C++ 20 feature was contracts. Since they were cut, he wonders what made them so controversial.
Okay, so contracts is a system for having compile time predicates evaluated. You basically say, this is supposed to be true. And if it isn't, something happens. And the design that I was co-designer of, and that was a design that everybody had agreed to, involved, you could say things were there just for static analyzers, you could say things were there for checking, and what happened when you had a violation, you called a violation handler, by default terminate, but that violation handler could also do things like write a log message and then terminate. And basically, those people who wanted more flexibility, they wanted to be able to continue after violation. Those people who wanted to optimize based on unchecked contracts. And so if you had a contract that says die if there's a dereference of a null pointer, they wanted the right to optimize away the dereference and things like that. So basically, at the last minute, everybody wanted everything. I mean, meaning somebody wanted in any one feature. And at the very last minute, it got stopped. People were not even willing to take a minimal approach because there were people who wanted their minimum thing in, which was not in other people's minimums. We were trying to design something that was the core facility that needed, that met essential aims, and nobody's got everything they wanted. And it turned out that that wasn't the case. Some people wanted something else. And the discussions is going on. I was in a meeting last night trying to do work on this. And it is not uncontroversial. Lots of people want things, but people with huge code bases into traditional computers don't actually seem to want exactly the same as people wanting contracts for embedded systems. And they don't seem to want the same as people who want static analysis of foundational stuff. It's those are the main things. So you have static analysis versus runtime analysis versus optimization. And that design space is difficult. I know where I would like to be, but I'm not going to get it, just like nobody is going to get exactly what they want. But we'll see.
We have a final question.
A final question, and if anybody from the audience wants a question, then one last.
Yeah. So someone asks, how do you check that new features do not have any fundamental contradiction with already available features?
We try to be careful. We try to implement, and we try to test it out at use. This is a practical exercise. It's engineering. It's not math. When I did the inheritance system for C++, I was a bit in a hurry, but I was very careful. It took me about a year. 20 years later, a group of people set out to prove it was wrong because they were in favor of Java and wanted to prove that C++ was a hack and it was unsound. So 20 years later, after I had put it in place, it was proven to be sound. Sometimes practice is way ahead of the theory, and you know, people are not going to wait for proofs. They're not going to wait for absolute guarantees. What we do is we do our best. We do the checking. We do everything that we can to get it done. And most of the time, it's not too bad. Ever so often, we make a change, but it's really, really hard to make a change once it's deployed. I mean, there's these 4.5 million programmers out there, and what if a significant number of them has used a feature and it was wrong? We try to fix it. There's been some problems with futures. There's been some trouble with the interaction between curly brace initialization and auto. They've been fixed, but that was very, very hard. The hardest problem we've ever had was when we changed from copy and write implementation of strings to the current small string optimization that is better in concurrency. That was really painful and took a decade. So we are very careful, and by and large, we don't get caught. That is, we don't make mistakes that can't be fixed or that, yeah.
There was a single last question here.
Yeah, you mentioned embedded quite a few times, and from 11 to today, that's really improved for embedded. But one of the main things that's still ongoing in the embedded space is exceptions, very prominent part of C++. Do you see going forward, if we want embedded to be more in the modern C++ camp, that we need to be more changing exceptions like Herb Sutter is proposing, or perhaps using a different approach like import freestanding like Ben Craig is proposing?
I actually think that there's two separate problems. One is the technical problems with exceptions, and then there's impression. And there is a lot of noise about how bad exceptions are, and I think a lot of it is noise. I don't think we should just throw away exceptions. I do not think that Herb's exceptions would actually solve the problem. By the way, Herb Sutter's exception is a system where you basically have a bit passed up the core chain so that you can test on it at the next level. The problem is, to a large extent, what happens for callbacks, because will the callback, how does the callback return, whether it was exception or not? What happens if I do exceptions and he doesn't do exceptions, all kinds of things. And then when you get a new solution, be it Herb's exceptions or expects, or there's 5 or 6 things, we get the n+1 problem. You have n version ways of doing something, you build the one true way, now you have n+1 ways of doing things, and the old ones don't go away. One thing that has bothered me a lot for the years is that exceptions have not been implemented anywhere near as good as they could be implemented. And so I think the first thing to do is to improve the implementations of exceptions. The other thing is that there really are 2 use cases, in my opinion. The one is where the caller can be expected to handle an error, in which case an error code is the right answer. And there's the one where you can't expect the immediate caller to handle it. And that's why you get all of these long chains of if-then-elses. You can make them implicit with language features, but there's still a long chain of if-then-elses. And when you start clogging the code, if you use exceptions just going up one level to the caller, exceptions are really bad. They are not compatible performance-wise with a simple return in a test. If you go up 50 levels, exceptions are really good. They run much, much faster than testing the same return code 50 times. And so I think we have to realize that and try and think our way through it. That is, we need interfaces that distinguish between an error that's expected to be handled and one that isn't. The simplest way I've seen that, which I actually happen to like, is the file system library for manipulating directories and such, that simply has all the functions in 2 versions. If you give it a place to put an error, then it will put an error there if it happens. If you don't, it throws an exception. So every function, like open a file, has 2 functions, one with an extra, without any extra arguments, it throws an exception, one with an argument that says, give me the error code there. And that's not that bad. It's yes, double the size of the interface, but it doubles the size of the part of the interface where it's relevant, and they're one-liners.
It's just an added argument that you could use. I think we should think much harder about these things. I've done some runs, other people have done some runs, and basically everybody who's looked seriously at it says sometimes exceptions win performance-wise, and sometimes exceptions lose. The thing that the embedded, what is it called, freestanding proposal does is it wants to get rid of the static overhead of having exceptions at all. And I think there might be a point for that, but I don't think they've gotten it quite right yet. I actually have, what is his name again? You named him? Ben what? Craig. Yeah, I actually have an email from him with a lot of details that I have to answer. So this is being done. This is being thought of. There was also a really nice paper by some people in England last year that shows how much better exceptions could be implemented, and basically taking away for a class of problems, taking away the overhead. Again, if you want to know what it is and you can't find it, send me an email and I'll dig it out. It should have been on my list of papers. I should have guessed these questions would come up and had the link to the answer, because this is actually a complicated thing. Everybody has a simple solution to their simple problem. But, you know, if you solve a nice problem for 1 million programmers, which is probably what you would get for a solution for error handling for embedded, well, there's still 3.5 million that might get harmed. I mean, there's a lot of code out there that uses exceptions and people are happy with them. And there are code that where they are not appropriate. I've written both kinds of code.
Thank you very much. Thank you for a great and inspiring talk. We have a little present here from Aarhus University. I hope it will go through the duty.
I can see some use for this.
So
yeah.
Thank you very much. It was
thank you.
a great pleasure to have you here and have the discussion with the.
Sure. I'll be back, and then I hope I can talk much more with people and see what work's being done here and such. But we have to get that virus get out of the way, or at least more under control than it is now.
Thank you very much.